that's just 12 out of thousands of different metabolic reactions that are possible in cells. So some cells will do some subset of those reactions. Other kinds of tissues will do their own specialized ones. Virtually all cells will do this, though. This is like a core pathway. So in different cells, different genes will be turned on to produce the different enzymes needed in that cell type. Okay, there's some properties of enzymes, but let's start with this part down here, just to make it clear. These are the ways in which enzymes are different from the catalysts that you can buy from a chemical company to do your organic chemistry. So biological catalysts are really special. But let's start with what's similar about them. Like any catalyst, they don't alter the equilibrium constant of a reaction. So we talk about favorable reactions that go downhill. So here's an overall reaction of fermentation. Glucose is a starting material, CO2 and water. Well, this is more than just glycolysis. This is the whole respiratory pathway used for Krebs cycle 2. Way downhill. So because there's such a large delta G, we say that's very favorable. A large negative delta G, highly favorable. The presence of enzymes speeds that reaction up. But the presence of enzymes doesn't make it any more favorable or any less favorable. That's determined by the level it ends at and the level it starts at. Enzymes don't change that. So if a reaction has an equilibrium constant of 1, that would mean that the starting material and ending material are at the same level, and the enzyme for that reaction might speed up the interconversion, but it doesn't make the product more favorable. It won't change the equilibrium ratio of 1 to 1. Okay, so that's one fact. Doesn't alter the equilibrium. And secondly, it doesn't get consumed in the reaction. So here's our standard enzymatic reaction. Enzyme plus substrate goes to enzyme plus product. The enzyme is totally unchanged. It's the same here as it was there. And when it's done with that reaction, it goes back and picks up another substrate and cycles through. Okay, so that's true of all catalysts. You could say that about powdered platinum that you'd use in an organic lab. It doesn't get used up in the reaction. Enzymes are a little different. They have to work at body temperature, physiological pH. So they have some special conditions, things that make them different from the inorganic catalysts that other kinds of chemists use for years. And these are the 3 properties you can point out that make enzymes very special catalysts. The first is how good they are at the job. They are just astoundingly good catalysts. You can enhance the rate, like if you compare the enzyme catalyzed rate to the uncatalyzed rate. It can be millions, billions of times faster, 10 to the 17th times faster. It's just astronomical rates of acceleration. So they're great catalysts in that regard. They're also great catalysts in that they're highly specific. So the kind of metallo-catalysts that a chemist would use in a laboratory setting are often non-specific. Maybe the same palladium powder or platinum powder you use to catalyze this reaction, you could use tomorrow on a different reaction. They speed up lots of different reactions. Not very good, but they speed up a wide variety. Enzymes are very specific about 2 things. They're very specific about recognizing a particular substrate and not attacking just any old thing that it encounters. So it's highly selective here as to what it chooses to attack. And it's also highly selective about the nature of the product This is also a difference between the enzymes and the non-biological catalysts. In the world of industrial chemistry, you throw in a catalyst in a vat, you generate some product, you feel happy if you got 80, 70% the product you desire, 30% side products. You don't see side products with enzymes. They make only one thing, none of this, mostly this and some of that, which is a good thing. Otherwise our cells would be filled with